everybody. This is the lecture for the chi-square statistic, which is our last new content for the course. And this material, I think, is some of the easiest of the course, so it's a bit rewarding to get to the end, so we can actually take it a little bit easy here, at least in terms of the amount of work, I believe. And so what a chi-square is, it's actually doing something that we haven't done before, which is actually looking at two nominal level variables. So if we have two variables and the way they are measured is nominal, this is a statistic that we can see is if there's some relationship between those two nominal measured variables. So remember, nominal is sort of where we're talking about categories. And so, for example, we could ask, do women buy more Macs versus PCs compared to men? So gender by type of computer. And again, this is the level of measurement. I'm a bit uneasy about this dichotomy of gender because it doesn't really exist in reality, but this is how we measure it sometime. And here we go back again with that dichotomy of women and men. Again, this is level of measurement. It's not the nature of the variable. So do women major more in psychology, dance, media studies, while men are more likely to major in business, physics, engineering? So we could actually do an analysis if we have data about this, and the analysis would be done by chi-square because here we have two categorical variables. So gender is used as a category here. There's not more or less of a gender. There's different categories. And then major. So there's not something that's more a major or less a major. There's just different categories of majors. And so again, the chi-square tests this. And basically what we're looking at here for our raw data is it's also quite different. We're just looking at counts of people. So the only thing we can do with nominal is count the people. We can't give them any scores. It's not like a major has a score if it's a psych major, et cetera. It's just a category. So the raw data is just counts of people who are in the different categories. So how many women are psych majors versus men, for example. And basically what we do in the statistic is that we compare the actual observed value, so the actual number of people who are in the different categories, versus expected values. And so based on the number, let's say it's men and women, and let's say it's psychology majors versus engineering majors, so two categorical variables. And so we'll get the actual counts, the actual number of people who are in those different majors, and identify themselves as men and women. And then we look at expected values. And those expected values basically come from, well, how many men do we have in general in the whole sample, and how many women do we have in general in the whole sample, and how many engineering majors do we have in the whole sample, and how many psych majors do we have in the whole sample. And based on those full numbers of number of men and women and number of engineering and psych majors, those total numbers, we derive with a very simple formula, which I'll show you later, expected values for each of the categories. And basically what the chi-square test is, are the observed, the actual number of people, different than what we would expect just based on how many men and women and how many engineering and psych majors we have? So where there's bigger differences between what really happens and what we expected just based on probability, then the chi-square is going to be larger. And we're likely to say, well, there's something there. There's something that's pulling the data in one way or another. If we have more women who are psych majors than we expect, and more men who are engineering majors than we would expect just based on numeric probability, then we start saying, oh, there's something going on here. There's something about the major gender relationship that is making it look different than what you would just expect just based on numbers. And so again, when our observations differ from our expectations based on probability, then something's going on. It's not just random. There's some non-random thing going on where people are going into one major versus another major non-randomly. And here's our formula. Just like with any other formula, don't panic. Just take it in. You can just look at it here, and chi-square is that little thing on the left. This thing right here is chi-square. What it's saying is basically we have cells. So let's say that we have men, women, and we have psych and engineering majors. So we have 4 cells. We have women who are psych majors, women who are engineering majors, and we have men who are psych majors and men who are engineering majors. So there's 4 cells. So what this is telling us is that for each of those 4 cells in this example, look at actually how many people are in that cell, and then subtract the expected, which we'll go into later about how to calculate this. Then we square that. Why do we square that? Because it could be a negative number. We could have fewer people in the cell than we would expect. There would be a negative number. So we don't want negative numbers. We want to square it. Because essentially, if we didn't have the squares, if you start adding up the differences between observed and expected, you would end up with a 0. So we need to square it so we don't have 0. And then we divide that by the expected for the cell. And this little thing, this little sigma, just tells us we're going to do that for every cell. And as we go through some examples here, you'll see it's actually, in some ways, very mechanical. It's just follow the steps and you'll get the answer. So let's look at this question here. Do married versus unmarried men vary in terms of the age of their death? So here we're going to look at 2 categorical variables, 2 nominal variables as we measure it. We're going to measure men in terms of being married or not married. That one's pretty easy. Married is a legal category, so we can actually see whether you're legally married or not. And then in terms of age of death, we could break that up into nominal categories. You might say they're ordinal, but we're just going to treat them as nominal in this case. So we can have people who have late deaths, people who have average age of death, and people who die early deaths. And so the hypothesis here, the null hypothesis, is that those combinations of being married or not married and when you die, they're not related. It's just random. Just however that stuff falls in the categories is just random. The HA is that there is something that's not random. Essentially that there is some combination of married, unmarried with the time of your death that is not random. So it's similar to an F-test in some ways in that we don't have a direction here. We're not making a specific prediction. We're just asking a question, is there some sort of non-random relationship here? So let's go through some examples. And so here's some observed data, let's say. So here on the left-hand side, we have one variable. We have the married, not married. So married, not married variable over here in the rows. And then in the columns, we have age of death. We have late death, average death, and early death. And by average death, we can just look that up for men. So look at your sample. If it's American men, what's the average age of death for American men? And then so you'll typically be given these data right here, these 6 cells. And then the first thing that you should do is you should total them. So you want to have the total of married men. So maybe I should just run through this real quickly. So we have married men dying a later death, married men who are dying at an average age, and married men who die early. And then there's not married men dying late, dying on time, and dying early. And then what we want to do is we want to total these. And so we add these 3 cells in this row to get the number of men who are married. So we have 64 married men in our sample. And then how many aren't married? So we add these 3 up and we get 33. So we have 64 married men and 33 not married men in our sample. And then we want to know how many people there are, so we can just add these 2 together. 64 plus 33 is 97. We have 97 total people in our sample. We also have the total how many people are dying in different categories. So late death is 30, average death is 45, and early death is 22. And so if we add these three numbers together, it also adds up to 97. So you want to get those totals for your rows and totals for your columns because we need that to do our calculations. And double check that you have that right by just seeing if they add up to the same total over here in this corner, the total number of people you have. Okay, let's look at the way to calculate the expected. So we have the observed already. So remember, we just need O and E for a formula. We just need the observed number of people in each of these cells, each of these combinations. And we then need also the expected. So these are our observed, the O. Now we need the E. The E comes from this simple formula. The E just says when you're looking at a cell, to find the expected number of people in that cell, you just take the sum of the column for that cell times the sum of the row, and you divide it by the total number of people. And I'll just take you through some examples if that's a bit unclear at the moment. Let's look at some data. So we have married men who die later right here. And so this cell, our expected value, sorry about that, every time I press on this laptop, it sometimes moves without me pressing anything. So in this cell, how many married men do we have in our sample? Well, we look down here, we have 64. So 64 is the sum of the row in this case. And then our sum of a column is 30. We have 30 people in our sample dying later than usual. So to find the expected for that cell, we just take 64 times 30 and divide it by 97. 97 is the total number of people right down here. So we calculate that, it's 19.79. Same thing for this. Married average death. How many married people do we have in our sample? Well, we have 64 married people. It's just right here in this row. How many die in average death? It's 45. So 64 times 45 divided by 97, total number of people. So the expected is 29.69. You do that for every cell. Let me just show you one more cell. So here we have not married and dying an early death. So how many people are not married in this sample? It's 33. How many people die in early death in our sample? It's 22. So the expected is 33 times 22 divided by 97, the total N. The expected value is 7.48. So when you're doing this, I've already showed you the first two steps. One is you want to get the totals of your rows and your columns and also the total number of people. That's the first step you do after you have the observed data. The second step is I would calculate the expected frequencies then using this formula. So again, each column and row for that cell, multiply those two numbers and divide it by the sample size. So for here, not married, average death, we have 33 people who aren't married, 45 people who die in average death in our total sample. And so we multiply that, divide it by 97, the total number of people. The expected value, the number of people, the expected is the number of people we would expect to be unmarried and die in average death based on just our total number of unmarried people and average death people in our sample. So we would expect 15.31 people to be here. So now we have the observed and we have the expected number of people for each cell. Now we just simply calculate things. So remember, the formula is the sum of O minus E squared over E. So I'm just going to take you through each little step. So let's get O minus E first. So I just take each little thing here. So married and late. Married and late, well, how many people were in there? The O was 24. Married, late, 24. So married, late, 24. What was the E? Well, let's go back and look at the E. Married, late, the E was 19.79. So we have 24, the observed, the actual number of people, minus the expected number of people, 19.79, 4.21. And then it's really simple from here. So just round to the second decimal place. There'll be some rounding errors. That's okay. We can live with it. So the O minus E is 4.21 for married and late. Then we simply square that. So 4.21 times 4.21 is 17.72. And so I see I have something on here. I'm going to correct this. Again, there might be some rounding errors, and that's okay. So actually, in the example I run later, I actually round everything to the second decimal place. This one's a little bit more third. That's okay. Either one is fine. So we take the 17.72, which was 4.21 times 4.21, 17.72. And remember, the last thing we have to do for every cell is we have to take O minus E squared, which we have right here, and just divide that by E. Well, where's the E from? Now we don't have to go to the other table. We see it right here, 19.79. So 17.72 divided by 19.79. So for that cell, this value of O minus E squared divided by E is 0.895. We can do the same thing for the next cell. So we have married and an average. So what was our O for married and average? Married and average is 31. So married average, the O is 31. And then what was the expected value? Well, the expected value is right here. Married and average is 29.69. So 31, the observed, minus 29.69. It equals this. This is the value of that, 1.31. We want to square that, so 1.31 squared is 1.72. And finally, we just have to take that value, O minus E squared, which is here, divide that by E, 1.72, divided by E. Well, where's the E? The E is right here, 29.69. So now for this one, for this cell, the value of this is 0.064. And then we can do the same thing for married and early. So married early, we have 9 people in the actual sample who are married and died an early death. So 9 is the O. What's the expected value? Well, the expected value right here is 14.52. So 14.52. So 9 minus 14.52 is negative 0.52. Keep track of the negatives here because we want to use that later. We want to kind of know the direction of the, are there more people than we expected or are there less people than we expected? We want to know that, so make sure you have the negative there, even though we square it and get rid of it right away. So 5.52 times 5.52 is 30.47. And so now we take that value, O minus E squared, which is right here, divided by E. 30.47, and we divide it by E, E is right here, 14.52. So the value for this term is 2.099. Then we do the same thing for the next row. So not and late. So not late, not late. We have 6 people in our sample. So 6 is the observed. What's the expected? The expected is right here, 10.21. So 6 minus 10.21, it's negative 4.21. You might be thinking, oh, well, what's the negative mean again? Well, just look at this, O minus E. So there's more people, we expected more people to be in that cell than there actually was. So there's fewer people than we expected. So there's fewer people who are not married and die late than we would expect just based on the probability of how many unmarried people and how many people who die late in our sample. So again, we square that. 4.21 times 4.21 is 17.72. Then we take the 17.72 here and we divide it by the expected, which is here, 10.21. So for this cell, the value of this is 1.736. So you do that for the last 2 cells. I think I don't have to run through everything now. I think you probably get it. And remember that our formula was the sum of O minus E squared over E. So the sum of it is adding up all of these things for the different cells. So I've highlighted it in red. we have to add these together. So if you add these together, we come up with 8.979, which is actually 8.98 if we round up. And we should round up to the second decimal place for our final numbers. In psychology, at least, and I think in social sciences in general, we round up to the second decimal place. So this is actually our chi-square. Chi-square is the sum of O minus E squared divided by E. So the sum of this for all the cells. So our chi-square is 8.98. So now we need to do a table. So for every statistic, we have to go to a table to find the critical value to test our HO. And so we have table B7 if you have the text. Or if you don't have the text, you can use this website. And that website is right here. Give me a second. So the website is right here. Oh, it was right there. Give me a second. For some reason, the news took over. I think I messed up here. I had it, and then the news somehow got back. And here it is. And so since we used the P is less than 0.05 level, so 5% alpha, we'll use this column right here. And the degrees of freedom is really easy. I'll make this bigger for us. So this is our chi-squared from our calculations. And then our table, whether it's in our textbook or that link, we use the degrees of freedom of this. It's the number of rows minus 1 times the number of columns minus 1. So we had 2 rows. We had married versus unmarried. So there's 2 rows. So 2 minus 1 is 1. How many columns? Well, we had a late and an average and early death. And so 3 minus 1 is 2. So 1 times 2 is 2. So we have 2 degrees of freedom. And we go here. P equals 0.05. That's our alpha. 2 degrees of freedom. 5.99 is our critical value for the chi-square. So we take our calculated value, 8.98 essentially when we round up, and we compare it to that 5.99 that we got from the table. We reject the HO. So there is some support that something's going on, something that's not random in terms of whether you're married or not married, if you're a man and when you die. And so, and it's at the P is less than 0.05 level. So what this means is it's again a non-random distribution. There's something going on that's making it a bit different for some categories of men in this case. So, well, what's going on here? Because the chi-square just tells us there's something going on. And there might be some formal tests. I don't know. There should be some formal tests, but they don't really talk about it a lot. Typically what we do is we just do an eyeball look at the numbers and see what's going on. And the best thing to do is go back to our table. So this is our table in terms of calculating the chi-square. So let's just go back here and let's look for the bigger numbers. What big? Well, what do you mean by bigger numbers? These things in red, because this is the chi-square. We add these together, this is the chi-square. So the bigger the number, the more contribution there is of that cell to the chi-square. So a big thing stands out here. Almost half of our chi-square comes from this cell, which is unmarried men dying early. Well, what direction? We have to look at the direction because we don't know it just from here, but looking at the direction that's positive, which means that there's more unmarried men who die early than we would expect. And by the way, this is based on literature. In terms of physical health in general, and in terms of age of death too, that men benefit from being married. You could think about it sort of in terms of gender roles and things like that, that men who aren't married might not be, for one, having the healthiest habits. They might be eating poorly and maybe not taking care of themselves very well. And perhaps there might be some thing why they might not be married, perhaps. Um, and the literature strongly suggests that in terms of heterosexual marriages, men benefit from being married in terms of physical health and things like that. Of course, this is not an experiment. We aren't randomly assigning people to be married or not married. So there might be other things going on uh, that might be a third variable that might be causing this. But the literature is actually quite strong about this in terms of heterosexual marriages. And then for women, they usually don't benefit much from being married. In fact, there's usually a detriment to their physical health compared to women who stay single throughout their life. So these numbers are based on that research. So there's a big number here. And there's a couple smaller numbers. There's a 2 here, so about 20% perhaps of our, I should say about maybe 23% of our chi-squares coming from this married early. Well, what does that mean? Well, I have to look at this again. So it's negative. So there's fewer married people and married men in our sample who die early than we would expect. So it's kind of the converse of here. So being married meant that there's a lesser probability of dying early in our sample. And then there's another one that's a little bit, it's not as big as the other ones, but there still seems to be something here that if you're not married, the chances of you dying later is smaller in our sample than we would expect. So there's fewer men in our sample who are unmarried and die late than we would expect. So it's a negative number here. So this is how we can actually incorporate it. And so actually my slides I'd put them in this order. I'm going to switch my slide order for you. And this is the write-up. So we have all of our stuff now. So a chi-square between marital status of men and age of death was found to be statistically significant. So chi-square, that's that little chi-square symbol. Then parentheses 2 is our degrees of freedom, comma, n equals 97. So we give the sample size of our total sample. Then equals 8.98 is our chi-square we calculated, and it was significant. We rejected the HO, so p is less than 0.05. Then if we were going to present this, we would have the observed frequencies in a table. So people can look at it and kind of see what it looks like in general. And then we then can explain it. So, well, what's going on? Well, this significant chi-square primarily reflects the observations that unmarried men were more likely to die early. Unmarried men were more likely to die early. This was the big cell here. Oops. Married men were less likely to die early. Married men were less likely to die early. And unmarried men were less likely to die late. Unmarried men were less likely to die late. And so these were the three things that seem to be pushing our chi-square to be significant. So I think this is relatively straightforward. So just real quickly, our assumptions for this test, we always have assumptions. Our assumptions that the observations are independent, which basically means whether somebody was married or not married was independent of the data of when they died, that somehow there wasn't something about our study that made those two things correlate. Our design was meant to be, they're independent variables, they're separate variables. Independent from each other. They're not IVs, they're independent from each other. And then the assumption also is that these observations are randomly selected from a population. So we're not picking people, or our sample's not biased to make the relationship look in a certain way. It's just a random sample. And then also there's an assumption that our expected frequency needs to be greater than 1. So we don't want to really run a chi-square if we have a 0 in our columns or our rows. So if we have a 0 in a column or in a row, we're going to have an expected frequency of 0, correct? Because it's the number of people in the column, number of people in the row, times the number of people in the row. So if the 1's a 0, we'll end up with a zero expected frequency. We don't want that. We can't run it like that. And it's better if our expected frequencies is at least 5. Um, we kind of violate that, I think, in our problem that we do next. But that's okay because I wanted to keep it simple and straightforward for you. So we'll not worry about that particular thing. And the actual observations can be quite low. It doesn't really matter. You could have one person. You could even have 0 people in a cell. It doesn't really matter as long as the expected frequencies are greater than 0, or preferably greater than 5 if possible. So it's not about the actual observations, it's about the expected observations. Okay, so here's a sample problem for you to do on your own. So here's the data. Pause the video, copy these data down, and run through the steps. So we know that the first step is you want to total the columns and the rows. And then you want to then walk through the steps that I just showed you. So let me explain these data real quickly. And so let's say that we did research and we got couples to come in, romantic couples. And we assessed each partner's attachment pattern, whether they were secure, the nice people to be in relationships, they can express their emotions, they can listen to you, they understand your emotions, they can communicate, they can give support, they can receive support, all that type of stuff. And then there's dismissing people who are avoid strong emotions. They can be very defensive about strong emotions. They didn't deny that they feel sadness or nervous about things. They tend to feel like they're superior to other people. So they basically dismiss the importance of relationships because they're so fantastic. They're great. If relationships happens, that's fine, but they're still fantastic regardless. And they tend to see their partner as a needy person, as an emotional needy person below them. And then we have preoccupied people who are nervous, anxious about relationships. They're the ones that are texting you all the time. They would be quite jealous. They think that you are sleeping around or flirting with people, or they need to know where you are all the time. Who are you with? What are you doing? Are you thinking about me? So they're preoccupied about relationships, and they're very uncomfortable not being in relationships. So they don't have a very strong sense of themselves, and so they need to have somebody else sort of define who they are. So we can ask, well, what happens with couples? Are certain types of attachment patterns attracted to other types of attachment patterns? If I can say it right. So the question of the chi-square is, so in terms of attachment patterns and the romantic couples we see out in the world, is it just random? Is it just random who you're with and the attachment pattern doesn't make a difference? Or is there something that's non-random, something that's systematic that draws certain type of people in terms of their attachment pattern towards other types of people? So let's say we collect data from couples. We bring in couples and we assess each partner's attachment pattern. So we have one partner here. This is one partner's attachment pattern. We'll do it as nominal. This is not how I do attachment research. I give people continuous scores on how secure they are and how dismissing, how preoccupied. That's really more of what the nature of attachment patterns are, more accurate. But let's just say we're doing it in an old-fashioned way, and we're just putting people as either secure, dismissing, or preoccupied. So this is one partner's classification of being secure, preoccupied, or dismissing. And this is the other partners. So one partner and then this other partner, their category. So these are the number of people who fall into those partnerships: secure and secure, secure, dismissing, secure, preoccupied, dismissing, secure, dismissing, 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 preoccupied, etc. So don't worry, we obviously have repeated combinations. So for example, there's 2 dismissing preoccupied cells. Let's not worry about that. Doesn't matter. We'll look at the data, see if there's something going on. That's fine. But that's what these data are. So one partner, which category are you in? And then the other partner in the columns, what category are they in? So pause and analyze these data using the previous problem as an example. Okay, so just as I mentioned before, the first step that you should have done is to do the totals. Totals for the columns and totals for the rows. So here we have how many secure people? We have 22 secure people here. And this is just based on this partner. So we're comparing these partners versus this partner. So we have 22 secure people, we have 12 dismissing, and we have 11 preoccupied. In terms of being, we'll call this partner 2. Partner 1 in the rows, we had 20 partner 1s who were secure. We had 10 who were dismissing and 15 that were preoccupied. Let's make sure we double check. Let's add our rows together. 45. Let's add our columns together. It's 45. So we probably didn't make a mistake. So now we take these numbers and we do the expected values. So I have all the data here actually in terms of the columns and the rows. So for partner 1 being secure and partner 2 being secure, we actually had 16 people, but what was the expected? Well, the expected was, sorry about this, 22, because we had 22 in this column, times 20, there's 20 in this row. 22 times 20 divided by 45, we had 45 total people. So the expected number of people in this, I should say couples probably, the expected number of couples is 9.78 in this cell. How about this cell? So secure, dismissing, so partner 1 secure, partner 2 dismissing. What's the expected value for this cell? Well, it's 12. Why 12? 12 is the column. 20 is the row. 12 times 20 divided by 45 couples, I should say. There's actually people. 45, no, it's couples. 45 couples. So 5.33 is the expected. So you do this for every single cell. I'll do one other one so you can see it. So preoccupied down here in the bottom. What's the expected? Well, we have 11 people in the column. We have 15 in a row. So 11 times 15 divided by 45 couples. And so the expected is 3.67. So here is all of our expected values and the formula that we used to get them and the raw numbers that we derived it from. So we're set. Now we have our O's. Our O is the observed. We have our expected from this table. Now we can do that final table. So in that final table, remember we're going to look at each of the combinations, row to column, each of the cells, and we have 3, 3, 3. We have 9 cells, so we should have 9 things here. 3, 3, 3. We have 9 things here. So for each cell, we're going to get O minus E. We're going to square that. And then once we have that, we're going to divide that by E to get our thing here for chi-square. So secure. So I'm going to go that chart. You can go either way, but I'm doing it this way. I'm going to do this row first, this one, and this one. Then I'm going to do this row, this one, and this one. And then this row, this one, this one, this one. You can flip it and do the other way. You'll get the same number. I'm just telling you how I did it so you can match things up. So secure, we have 16 people. And we have 9.78 as the observed. So secure, 16 minus 9.78, the expected, 6.22. 6.22 times 6.22, 38.69. That's our O minus E squared. We take that, we divide it by E. Our E is right here. And so 3.96 is the value for this cell. for this ratio right here. So let's look at another one, dismissing secure. So dismissing secure for me is this one. Dismissing secure, we have two people there, or two couples, I should say. And then we have an expected of 4.89. So dismissing secure couple, two observed, 4.89 expected. So it's negative because there's fewer actual couples than we expected in this dismissing secure category. And so it's negative 0.289 for O minus E. 2.89 times 2.89 is 8.35. 8.35 divided by 4.89, the expected, is 1.71. Let's take one last one. So let's take the preoccupied secure right here. There's four people in our sample, or four couples in our sample that were preoccupied for the first partner, secure for the second one, and the expected value for that cell was 7.33. So preoccupied secure, there was four couples, but we expected 7.33 couples there. So there was 3.33 less couples than we expected in the preoccupied secure. There's fewer actual couples there than we expected. 3.33 times 3.33 is 11.09. 11.09 divided by 7.33, the E, 1.51. So here are all the numbers. So if we add this, it's a whopping 31.94 for the chi-square. This is what we call making up data. Even though the data are in the direction of the research, it's probably not as strong as this. But these data are made up, obviously. And what I did here too is before I got off this table, I thought, well, why don't I look at what's going on here? Which things are really contributing to it? And there's some stuff here. There's a couple things here. I didn't really talk about this in the interpretation because it's only maybe 10%, maybe 20% of the stuff going on. You could add it if you want to, but what really stood out was these. There's a 9 and there's an 8.52. I mean, really higher than the other stuff. More than twice as high as anything else in terms of contributing. And they actually link towards the same direction. So the 9 is preoccupied partner number 1, dismissing partner number 2. And guess what? The 8.52 is just the opposite. Partner number 1 dismissing, partner number 2 preoccupied. So there's something here about the dismissing preoccupied that's going on that's really driving this. Well, what's driving this? Well, what's driving this is, let's leave the direction first. So there's more dismissing preoccupied couples than we expected here. And same here, there was more preoccupied dismissing couples than we expected here. So dismissing preoccupied pairings seem to be really pushing the chi-square. If you want to interpret this, you can also. So secure, there's more than we expected. So secure people went to be with secure people. Big surprise, right? And then the other thing that's sort of going on is you can also talk about this if you want. We have a 3.52 here, and then everything else is pretty small after this. But 3.52, there's a secure dismissing. Well, what's the direction? There's fewer secure dismissing couples here than we would have expected. And so it's a negative thing. So there's something going on, at least here with partner 1 and partner 2, that there's fewer than we expected. Let me kind of look down here. And it's the same here too. When we look at partner 1 being dismissing and partner 2 being secure, there's fewer than we expect. So you could also talk about that if you want, that there's fewer secure dismissing partnerships. And you can imagine why that might be. A secure person probably won't put up with the crap of a dismissing person. I should say the crap of it, but you know what I mean. It's probably not nice to be in a relationship with a dismissing person if they are so distant emotionally. They don't help you out when you need them, and they're putting you down as being stupid and silly and emotional. Probably for you, it's not a good relationship, not a satisfying relationship. Should say it that way. Shouldn't say bad or good. I should say not satisfying. And so that's really what's going on in the numbers here. So we haven't tested the HO yet, so we just kind of been looking at the table. So let's test the HO. So our degrees of freedom is we have 3 rows. So we have secure, dismissing, preoccupied, -1. And we have 3 columns, secure, preoccupied, and dismissing. So it's 3 minus 1 times 3 minus 1. So it's 2 times 2. 2 times 2 is 4. So we go to the table, and we go to degrees of freedom of 4. And this is the, P.05 right here. 4 degrees of freedom, 9.49 is our critical value. This one's almost a no-brainer. So our calculated chi-square of 31.94 is way greater than this critical value, so we reject HO. So there's something going on here. There's not a random pairing of couples in terms of their attachment patterns. It's not random. There's something non-random, something systematic that's driving certain types of couples, certain types of people to be in relationships with other certain types of people. And so we can write it up. And so a chi-square tested whether romantic partners' attachment patterns related to each other. This chi-square was significant. Chi-square, parentheses 4 degrees of freedom, n equals 45. We had 45 couples. And in our chi-square that we calculated, 31.94, it was a rejection of HO. So it's P less than 0.05. It's significant. And then I wrote a pretty simple thing here. So there's a reference to the table 1 for the observations. And then the significant chi-square largely reflects the tendency for preoccupied and dismissing individuals to form romantic pairs. So this actually follows the research data, even though it's probably not as large of an effect as I have here in the made-up data. But basically what happens is that these individuals meet each other's expectations about the world. And so a dismissing person likes to think of themselves as being in control and being above other people. And who better to have a relationship to confirm those beliefs than a preoccupied person who's very nervous. And so a dismissing person loves to be in a relationship with a preoccupied person because they can put them down. They can derogate them, say they're stupid, say they're emotional, feel in control, because the preoccupied person, unfortunately, will often put up with that type of nonsense because they so much want to stay in a relationship. They're so dependent on other people that they will put up with more crap because they feel that dependency. And so it meets the dismissing person's view of the world, and also unfortunately, it kind of meets the expectations of a preoccupied person's. So a preoccupied person's view of the world is that they're out of control and they're emotional, and they need to fight to keep relationships going. And maybe a dismissing person will, in some ways, also put up with that type of stuff because they're not invested. So if the other person's screaming and yelling at them, they're like, okay, what's wrong with you? It's nothing with me. And so a dismissing person, because they are so emotionally distant and defensive, maybe can sort of just sit there while the turmoil is happening around them. And so for the preoccupied person also, preoccupied people tend to think they want to save somebody, that they can change their. You see this a lot in heterosexual relationships, although it certainly occurs in same-sex relationships too. But you can hear I can hear the preoccupied people that I've seen in interviews proclaiming they can change their partner. The partner needs saving. They can change them if they just stay with them long enough, and they'll change them into some sort of beautiful partner. That's not a great belief to have. So in essence, these couples tend to stay longer together with each other, even though they have low satisfaction in their relationships, because they meet each other's sort of expectations of the world and what relationships are. And the data actually are probably pretty much aligned with the research. So secure people tend to be more towards each other. Um, Secure people will more likely be in relationships with a preoccupied person versus a dismissing person. A preoccupied person, at least you have somebody who cares about the relationship and has some emotion. And secure people can try to work with that, if you will. Whereas a dismissing person, a secure person probably will say, "Forget this. This is not the relationship I want. You can go off and be on your own if you want to. This is not for me." Um, and so the data here kind of reflect the research. But again, I think the data strongly suggests this. These pairings of dismissing preoccupied people are just as frequent as the secure, and they stay together just as long. It's just that the satisfaction levels differ significantly. Okay, I think we're getting towards the end of this. So a simple write-up like this is good. And then there'll be a homework and an SPSS lab for this topic that you'll need to do. So this is our final lecture. So take care.